Yes.
Okay, so we just talked about how to generate keys. And once you have keys, then we already understand how to do encryption. But there are a few other things such as signing documents, which require more thought. Okay, so we'll talk about that now. So the in order to um, sign a document, so what is a digital signature? What properties do we want from a digital signature, right? So first of all, you want to make sure that the receiver can verify who actually sent or signed the message, okay? And then the sender should not be able to come back later on and say, well, they never signed this document, it must be a fabrication, right? It should not be possible for the sender to claim that this is a fabrication. And thirdly, the receiver should not be able to generate the signature on their own, right? Because once again, obviously the second and third points are somewhat related because both of them relate to whether the message the signature can be fabricated or not, okay? And it's fairly easy to understand why conventional crypto is not that useful here, because both the sender and receiver have the same key. Therefore, whatever the sender can generate, the receiver can generate. So, so you can't have the third property where receiver is not able to generate the signature. Okay, so we generally rely only on public key signatures. And how to sign, we kind of talked about it, at least in the abstract, when we introduced public key cryptography, and that is the originator simply encrypts a message using their private key, right? But this is conceptually this works because only it ensures the authenticity of the message, but the problem in practice is that encrypting the whole message for the purpose of signature is once again too inefficient, right? Because as we said, any document you can think of it as bulk data, and bulk data encryption is quite slow. So what we do is we use what are called hash algorithms in order to compute a small hash of a large message, right? So you take a big message that could be kilobytes or megabytes or whatever, and then you compute a fixed size hash value on that, and the hash value could be 128 bits or 256 bits or something like that, and now you basically encrypt just this hash. Okay, so this way you're not using public key cryptography on bulk data, you're just using it on a small 256 bit block or 128 bit block, and that's very much feasible. So in order to use a hash function this way, right, you need to have again certain properties for this hash function, right? So given this message P, which is again we talk about this as a bulk data, a large amount of data, you should be able to compute a hash on that fairly efficiently, right? Obviously, it should be much faster than say encrypting it using public key cryptography, right? So it should be much faster than that, right? It should also be the case that because the hash value is available, you generally don't want the hash function to be invertible, but more importantly, you want this property that is called collision resistance. Okay, so collision here means that two messages end up producing the same hash value, and that's the collision here. And when collision happens, then if you have a message M1 and M2, and let's say hash of M1 equals some X, and hash of M2 also happens to be X, right? So that is what we call as collision. And when this collision happens, what that allows the attacker to do is to switch between M1 and M2, right? So the sender, in this case, the sender could be the attacker. The sender could send you M1, right, followed by H of M1 encrypted, right? Encrypted using the sender's private key. Now, what happens is that then later on, some attacker could replace it with M2, and because this encrypted part is going to be the same because the hash values match, so an attacker can substitute M1 instead of M2. So for instance, you might be, the M1 might say Alice owes certain money to Bob, and that could be replaced with M2, which says it's not Alice that owes the money, it's Bob that owes the money to Alice, right? So this kind of message switching can completely change the meaning of the whole document. And so it's really important that there be no way for anyone, either the sender or some attacker, to be able to craft two messages, M1 and M2, such that they both produce the same hash value, right? So this property is called strong collision resistance, meaning that an adversary cannot generate two messages that have the same message digest. There are many common hash functions. MD5 used to be considered secure at some point. Then SHA-1 was considered okay. But now in SHA-160 is considered secure. So the understanding of what is secure changes over time as we, as a result of it changes for two reasons. One is that machines get powerful. We get custom hardware that can do, compute these hash functions very fast and so on. And secondly, because as people understand these algorithms better, they find attacks on them. And so as a result of this, what we consider as a secure hash function, evolves over time.